All right, let's get started for today. A couple of announcements. Your projects 5 are due on Friday at 5 p.m. Your homework 9 has been released yesterday and will be due Monday at midnight. Homework 9 is your last homework. Enjoy it while you can. Or, there's a drop the lowest policy, but I highly encourage you to make all your homeworks to prepare for the exams. Any questions about logistics? All right, let's get started with technical topics then. Today we'll look at Naïve Bayes. This will be our first lecture on machine learning, which will be the topic for the remainder of this course. So up to now, what we've looked at is how to use a model to make optimal decisions. In machine learning, we'll look at how to acquire such models from data or from experience. This model acquisition could happen in many ways. It could be learning probabilities, which we've actually seen a little bit of in model-based reinforcement learning. It could be learning structure. For example, learn the structure of a BaseNet graph. Or it could be learning hidden concepts, as you would do in clustering. Today, what we're going to look at is one specific task, namely classification. And the way we'll tackle classification in today's lecture is in a model-based way using Naïve Bayes. So what's classification? Here's an example problem. Let's say you want to build a spam filter where the input to your system would be a new email coming in. The output your system is supposed to produce is a decision whether that input is spam or ham. Ham being desirable email, spam being undesirable email. So the way you'd set this up in the machine learning context is you would get a large collection of example emails, each of them labeled as spam or ham. Note that somebody has to do this work. So somebody would have to go in, collect a large amount of data, label them as spam or ham. If you have people using your email system, maybe they would help you as they get an email that they don't like. They might mark it as spam, help you train your system. If you start from scratch, you somehow have to collect that data. Then what you want to do is learn to predict for future emails which class they belong to. The first thing you'll have to decide on, is a set of features. So features are the attributes of what you're getting, in this case, emails that you're going to be using within your learning system. So in the case of classification for spam versus ham, you could say, well, one set of features I'll look at is what words appear in the email. But it could be more to it. You could extract text patterns and check whether there's an appearance of a $sign in the email. You could check if there are a lot of capitalized words in email and so forth. All of these could be features. There could be non-textual features such as, is the person who sent that email in my own contacts lists? And so in some sense what's happening here is the input that you get, the email, is bottlenecked through the set of features that you compute from that input. And that set of features is what's then going to be used by the learning system to make a decision. So picking good features is really important. We've seen this in the case of reinforcement learning for Pac-Man and in looking at evaluation functions that were weighted sums of features. Same thing here. You pick features that are rich enough, you might be able to represent what you care about. Of course, if you put too much in your feature space, maybe it'll be hard to learn if you only have a limited amount of data. We'll get back to that a little later. So what you'd hope from your system is that if you then get these emails coming in here, first one, dear sir, first I must solicit your confidence in this transaction. This is by virtue of its nature as being utterly confidential and top secret. Hopefully classify that as spam. Next one, again, hopefully classify that as spam. And then the next one looks like an email to a support desk or a friend where they're really expecting a reply, and it might make sense to send a reply, and hopefully that'd be ham. This is just one example. This is classification of email. Here's another example, digit recognition. So the input here would be images, which formally are a set of pixel values or a vector of pixel values. You'd have a grid, maybe 8 by 16 grid, and for each of these 8 times 16 pixels in that grid, you'd have a value, maybe 3 values. If it's color, you get RGB. If it's grayscale like we have here, you'd get 1 value per pixel saying how dark that pixel is. The output you're supposed to produce, or your system is supposed to produce, is a classification of what digit you're looking at. So for example, for this set of inputs here, you might hope for a 0 for the first one, then a 1, a 2, a 1, and maybe not so clear what the last one is, but it's something that somebody intended. Hopefully you can label it accordingly. The setup would be similar. Again, this is generic classification setup. You start with collecting a lot of data somehow about the task you care about. So in this case, you get a large collection of example images, each of them labeled with a digit. So it's images with corresponding labels. Again, somebody has to provide these labels. So you might do that yourself if you're building your own system. You might be able to find a data set where it's already done for you. Or if you need a lot of data for your task and maybe you have some money available, you hire people to do it for you, maybe through Amazon Mechanical Turk. And then from that training set, we want to learn how to predict labels of new future images. Again, the classifier will work through feature space. So we'll have to define a set of features, which are the attributes that we think matter to making the decision. You could keep the raw pixels as part of your set of features, but you could include more. You could think of things like shape patterns. What's the number of components in the image? What's the aspect ratio of the space where there's something written? What's the number of loops that's been formed? And so forth. Maybe if you had live handwriting, you could say, what's the number of strokes executed while writing this digit, and so forth. So again, this will bottleneck your decision making, and so you need to be clever about what you pick here for your classifier to have a good chance at succeeding. But there's some other classification tasks. So in general, a classification task is something where you have some inputs, X, and you're supposed to predict one of a set of possible labels, also called classes, Y. Okay, so we already looked at spam detection. The input was a document, the class is spam or ham. Optical character recognition, very similar to the digit recognition. The input would be images, and the classes you predict would be characters for English, 1 out of 26 letters. Medical diagnosis, the input could be symptoms of a patient, and then the classes that you're choosing among are possible diseases, or maybe that the patient has no disease. Automatic essay grading, the input here would be a document, and the output would be a grade based on what you saw. Fraud detection, this is commercially quite a big one. You might sometimes get a phone call from your credit card company or a text message saying, can you please confirm this transaction? What happened is they have a machine learning system that's classifying transactions as maybe fraudulent or legit. If they think it's maybe fraudulent, then they'll follow up with you to make sure indeed you attempted to do that transaction. Customer service email routing, you send an email somewhere, there are different people who are qualified to answer different questions, so it could be automatically routed if you have the right system to the right people to answer your question, and many more. In many ways, classification is probably the most widely used machine learning technique and maybe even AI technique right now in industry. So it's a very important commercial technology. We'll look at it today. We'll look at it next lecture. Today, what we're going to look at is a model-based approach to classification. Next lecture, we'll look at an approach that doesn't assume building a model first. So what's model-based classification? The idea here is that you build a model, which could be a BaseNet. In our case, this will be a BaseNet, but it could be something else in other classifiers, where both the label and the features are random variables. And so what you're building here is a probabilistic model, in this case where if you were to sample from that probabilistic model, you'd hope that it would generate a distribution over labels and features that matches up with your training data, because then that would mean that your model really captures how that data was generated. Then at testing time, you would instantiate any observed features, which could be all features, but maybe sometimes some are not computable from the data you have, so some would be hidden. And then you can do a query in your basenet, ask it for the posterior distribution over labels given the features you observed. Then that distribution would tell you what decision to make. It could potentially even tell you that there's a lot of ambiguity because there's a close call between a few classes. And then based on that, you might make your decision. A couple of challenges here. So first challenge is to choose the structure of the basenet. Right? There are many choices if you have a set of random variables in terms of designing a basenet that involves them. We need to pick one of those options. And then the second question will be how we'll learn the parameters. Note that in principle, basenet structures can be learned too, but that's beyond the scope of what we'll look at here. Here, we'll choose the structure and we'll learn the parameters. So here's a first example of a basenet that we could use, and actually the most commonly used one for classification. It's this structure here. What are we looking at here? Y is the random variable corresponding to the class or the label. And then F1 through Fn are the random variables corresponding to each of the features. So what's encoded here? It's saying that once we know the classification label, each feature is generated independently. It's a very strong assumption, right? And it's typically violated for pretty much any data you'd ever be working with. But nevertheless, this model often will perform well despite it violating some things that are true in the real world by making pretty strong independence assumptions. Okay, so for the simple digit recognition problem, you'd have one feature for each grid position in your image, and that feature would be the pixel value there. So a number, maybe a real number, or maybe a number from 0 to 255 if your grayscale is digitized. Then this feature value could be even further discretized if you wanted to, whether it's on or off based on whether it's below or above 0.5 or below or above some average number that you think is the background. And then so each image will map to a full feature vector. And the full model is the product of the conditionals of each feature value given the class label multiplied with a prior over how often each class is likely to occur. What we'll need to learn here is the parameters in this prior and the parameters for each of the features conditioned on each possible class label. Okay. Why is this quite naive? Aside from the name, well, think of it, let's say you are writing out a digit, let's say the number 2, and now you shift it over a tiny little bit, your 2, then all pixel values that activate will be shifted over accordingly. And so clearly, once you decide on writing a 2, which pixels are active or not active is not independent of each other. There's a strong correlation there, even once you know it's a 2, in terms of which pixels will be active, which ones will not be active. Well, this is assuming it's all independent. So you'd have to externally somehow normalize for that. You might have to do something ahead of time where you carefully align your digits, make sure they're nicely centered, nicely lined up, and then these assumptions might not be as bad, and this system would actually work pretty well for a lot of problems. But keep in mind that this is a very strong assumption that your features are independent given the class label. How do you make decisions with this, right? So what's going on here? We have a joint distribution specified in this naive Bayes model. We don't have to specify a whole lot here, right? If we compare learning the full joint distribution, which would require us to learn y times f to the n values, to this over here, where we only have to learn for each feature, so n times, a conditional probability table with number of entries equal number of class labels times number of values that feature can take on. So we have a much smaller, in this case, linear in n, which is the number of features, number of parameters, compared to exponential in n if we learn the full joint distribution. So here's another reason why Bayes-nets are a more practical representation of full joint distributions, because you can imagine if you need to learn all these parameters, learning an exponential number of parameters and the number of features will be difficult to do, because when you want to learn something, you need data to back it up. And if you want to learn a lot of things, you're going to need a lot of data to back it up. And exponential is usually not practical to achieve in whatever computation or data collection you need to do. So all we need to do is specify dependence of each feature on the label. So the total number of parameters linear in n, which is a good thing. It's a very simplistic model, but the beauty is that we get this linearity in n. So what does inference look like? Well, assume we have some observed set of features, f1 through fn. We can write out the probability of each label jointly with those feature values. That's actually quite simple to do. That's just this product over here. And then we can compare those. Whichever has the highest is going to be the class label that's most likely. We can actually compute the probability by summing these together, which gives us the normalization constant. And then we can divide each entry by the normalization constant and get the probability of each class label given the evidence we observe. Okay? So then we have a distribution that tells us the probability of each of the labels. Any questions about the procedure here? All right. So what do we need in order to use naive Bayes? Assuming somebody gives us the model, what we need is an inference method. We just saw that part. And it assumes you have some probabilities available to you. You use standard inference to get the conditional of the label given the features. Nothing new really there. The new thing is that we also need estimates of those local conditional probability tables. We need an estimate of the distribution for y. Then we need an estimate of the distributions for features given the labels. And these we will call the parameters of the model and generically represent by a parameter vector theta. So theta here is a vector with an entry in theta corresponding to each of the entries in py and each of the entries in each of these conditional probability tables. It's all stacked together in one vector theta. And that's what we'll be trying to find by learning it or estimating it from data. For now, we assume that the probability fairy would bring probabilities to us and we just use them. But typically they'll come from training data. And the simplest way to get them is to use training data counts. What that means is that effectively you just look at how often did each class label appear. Then the fraction of times label 1 appeared is the probability assigned to label 1. The fraction of times label 2 appeared is the probability assigned to label 2, and so forth. And then for the conditionals, you can do the same thing. You can say, when it was class label 1, what fraction of time was the pixel on, what fraction of time was the pixel off, and make that your probabilities of on and off given that particular label for that particular pixel. So very straightforward, similar to what we did when we were estimating transition probabilities when we were looking at model-based reinforcement learning. Exact same type of calculation. You just count things up. Now, what we'll look at today as we go further along is that this can be a little naive to do things that way, and we'll look at better ways of doing this. Let's for now assume that that's a way for us to get these conditional probabilities as well as the prior for y. So what would that look like? Then you'd have some digit. There would be some prior distribution, py. Maybe we think each digit is equally likely. We know in practice that's not true. The zeros and the ones are much more likely, and in general the lower numbers are more likely to appear, but for the purpose of this class, let's assume it looks like this. Then we have for each pixel, so we have many of those tables, an encoding of what the probability is of that pixel being on given a specific class label. In this case, maybe the class label 3, but you'd have a table for each of the 10 possible class labels and each pixel. So this repeats many, many times. So that's one model we could be working with, a very concrete example. This is the generic naive Bayes model. For text, it turns out we use something a little different, or people typically use something a little different. It's called a bag of words model. The features for text will be the words at each position I. So you start at position 1, 2, and you keep going. As before, we're still trying to predict the label of what's in that text, spam or ham. As before, we assume they're all independent of features given once you know the label. But the novelty here is that we'll assume, that's the bag of words assumption here, that's the new part, that each WI is identically distributed. Meaning that if we look at the generative model, including the joint distribution here, each conditional of a word given the class label is drawn from a conditional probability table with the exact same numerical entries. So now we just specify one conditional probability distribution and a prior distribution. We've seen something a little bit like this before. When we looked at Markov models, we were looking similarly at a Bayes net where we had an initial state distribution, quite similar to the class distribution here. And then for every next state, the conditional of the next state given current state was using the same conditional distribution table for every time step t. Same thing here for every entry in that document. So every word for any position I, the conditional distribution of seeing a particular word there given the label is the same independent of position in the document. Is that a realistic model? If you sample from this, will it look like real text? Not at all, right? It's not going to look like real text because it doesn't understand that certain words follow each other more likely and so forth. But it turns out for classification, even though it's a very crude approximation, it'll still work quite well in many cases. So keep in mind, I here is indexing over entries in the document in the bag of words model. So each entry in the document corresponds to feature, and the possible values that entry can take on is the words you have in your dictionary that you're willing to consider for this piece of text. And you might have an extra word in there that says all other words or something. Okay, now this is often called tied distributions. What that refers to is that in your Bayes net, the conditional probability tables are not just all chosen separately, but there's some connection between them. In this case, a very strong connection that table for word I or entry I in the document is the same as entry I plus 1 and so forth, essentially for all I. The reason you can think of it is as a bag of words model, but in fact, this model is often also used for other tasks that don't involve words at all. But the bag of words model here, pictorially think of it as you're given a document, and once you use this model, you might as well throw all the words in your document in a bag and pull them out in a random order after that, and that new document that you just generated will be interpreted the same way as the original document by this type of model because it doesn't consider order in any way. So for this type of model, if you're wondering, well, is it realistic to expect this model to do well? You could take a piece of text, randomly permute all the words, look at it and see if based on the random permutation of all words, you can still make sense of whether this is spam or ham. If you think it becomes completely impossible to make sense of that for you, and especially for a computer maybe, then this is not a good model. If you look at that bag of words, you say, well, I can still recognize whether it is spam or ham, then this might be a great model because you're simplifying things, meaning you need less parameters, but you're still retaining the essence. You're still able to understand whether it's a spam or a ham message. Okay, so spam filtering. What would it look like? Our parameters would be a prior for the class, distribution for word given spam, which is the first class label, distribution for word given ham, which is the second class label. So it might look something like this. Maybe 2/3 is ham, 1/3 is spam. Then there's some distribution over words given spam. What can be meaningful after you've learned this is to look at those distributions and look at which are the most prominent words appearing for each type of email to sanity check that what you found might make sense. Do the same thing for ham. Seems like for both of them, the is the most frequent word, the most likely to be chosen, then to, then and, of. So in fact, a lot of the words appearing here so far are not all that discriminative between the two, because this is just a generative model. It's not saying to indicate something is spam, this is the typical word being chosen. It's saying if somebody writes a spam message, then this is how likely it is for each word to be chosen. Okay, so where do these tables come from? For now, let's assume we just do counts. So we look at our data, we look at all the spam messages, and we count how often the word the appears. Apparently it appeared 0.0156 of the time. 2 appeared 0.0153. fraction of the time, and so forth, and those are the numbers we put in there. So you collect a large corpus of that kind of data, and there is your table after you run some counts. So how does classification work with this? Let's say you get a new email coming in. You would first look at the prior as we're accumulating all our information here. The prior says 0.33 spam, 0.66 ham. Remember, our inference procedure is something where we're computing the product of each label with then the product over all features, the probability of the feature, in this case, word I, given the class label. And then we might normalize, but normalization doesn't affect which label wins this kind of product tally. So start with a prior. We see a first word, Gary. Probability of Gary given spam is pretty low. Given ham is low too, but a little higher. And we see now that this tally changes here. What are we looking at here? These entries here are the log probabilities of the numbers that we've seen so far. So it's the sum of the log probabilities of the numbers we've seen so far. Why might you care about that? Well, if we looked at just this running product over here as we build it up, it'll essentially go closer and closer to 0 as we go along. Taking the log of something is monotonic. If the original number is higher, the log of that original number will also be higher. And so we might as well work with the log. This puts things on a better scale. We'll have numbers that we don't see go to 0 and lose all our information. So here we have a running tally of the... Now, if you take the log of a product, it's the sum of the logs, so that's why we end up with a sum of logs of probabilities that we're tallying here. So we keep going. See, at this point, ham has the better score, minus 16, which is better than minus 19. Keep working our way through, adding on the log probability of this particular word given the class label. And as we go along, we end up with, in this case, minus 80.5 for ham, minus 76 for spam. Minus 76 is actually better. And actually, we can reconvert this into probability. These are logs, but you can do a conversion back into probabilities by essentially computing e to the minus 76 and e to the minus 80.5. And then you need to normalize these. So the normalization constant z will be the sum of those two, and you then divide by that to get this number. Now, you might run into trouble with numerics here. So in practice, little trick you play is you actually, since you can multiply whatever you want here, it'll stay the same. You can effectively just look at, if you start this, instead of computing e to the minus 76 over e to the minus, stick. It's not sticking there. Let's try it over here. So a little practical trick is when you compute this, instead of computing directly this over here, which would be the probability of spam, given all the features you observed and given the prior, you can multiply top and bottom with e to the plus 76. So we multiply with e to the plus 76, top and bottom. And so what happens is this cancels out to be 1. If we do the same thing here, we have 1, and then we have plus e to the minus 4.5, which actually becomes numerically computable on your machine, and you'll get a reasonable answer as opposed to some kind of 0 over 0, which it doesn't know what it would be. But so that's in practice how you get this number out here, which apparently is 98.9% probability that this is spam, based on what we saw here. Any questions about the procedures so far? All right, then let's take a break here, and after the break we'll look at training and testing in detail. All right, let's restart. Any questions about the first half of lecture? Over there, yes.
Training data, is it better to make your classifications that are new and add them to training data also?
So that's a great question. Let's talk about that on the next slide, because you're anticipating what we'll be talking about on the next slide. All right, so let's jump to the next slide. Here's a picture to keep in mind. In lecture and homework and projects, you're being trained. Then you take a practice exam, which is a check that hopefully tells you how well you might do on the actual exam. Then what might happen is that you decide that score you had on the practice exam where you tried it wasn't all that great. You need to change something about your training. You go back, you retrain yourself. You take a new practice exam to say, you see if you satisfactory performance now. If so, you call it good. You go on to take the real test, which is the final exam. And that's essentially the machine learning cycle done by students, hopefully. But this is effectively what it looks like. Think of held out data, the held out data box as the practice exam, and think of the test data as the final exam, and you get the same principle here. So what's happening? You get some data. Those are labeled instances. This could be emails marked as spam versus ham. This could be digits labeled with a number and so forth. Next step is to split this entire data set that you got into 3 subsets that are disjoint, no overlap. The biggest one will be your training data set, and then there will be 2 smaller ones, your held out data and your test data. Maybe a typical thing could be take 10% to be your test data, maybe 20% your holdout data, and 70% your training data, just to give you a ballpark figure. Then, of course, you look at your data, you decide on features, which are, in some sense, the way you'll bottleneck your data before you feed it into your classifier. You start with the experimentation cycle. You train your parameters. So what that would mean in the naive Bayes setting is you would run a count to extract the conditional probabilities for each of the tables. That would be the learning. But you only use the training data, not the other data for this. Then you tune your hyperparameters on a held out set. What do I mean with hyperparameters? Those are the external choices you're making. For example, are you going to use a bag of words model or not? You can try both. Are you going to use a naive Bayes model or maybe a model with more edges in it? Might be yet something else. It might be, are you using maybe a perceptron, which we'll cover in the next lecture, versus a naive Bayes? There are also some continuous hyperparameters that we'll get to later that you somehow have to set to some real value. You have to pick some value there. So you'll pick something, and then after you pick something, you evaluate on your held out set what the accuracy is. But you'll do this for many, many choices of those hyperparameters. And then you'll pick the choice of hyperparameters that performs best on your held out set. Once you've done that, To evaluate the performance of your classifier, you then check how it does on the test set. You report that number and you say, well, if anybody were to feed me new data in the future, the accuracy on the test set is likely a reflection of how well it do on new data in the future. Of course, for this to be a fair estimate, you can't peek at the test set ahead of time, because if you do, you might effectively start overfitting and tune your classifier to the test data specifically, which then wouldn't be representative of new data you haven't seen yet, right? So most of your time will be spent going around essentially over here, where you run your training, find your parameters, evaluate on your held out data, and go back. I mentioned a few choices. There's another choice you make in this cycle, which is the features. You might decide that you need new features, different features, more features, less features. Those are all kind of encompassed in this tune hyperparameters cycle, where you check on the holdout set which choices there do best. And then the idea here is that since you don't fit your actual parameters on the holdout set, the performance on the holdout set will be fairly representative of the performance on the test set. And the performance on the test set, since you'd never use the test data, will presumably be representative of the final performance you get on data that comes to you in the future. Okay, so evaluation would be fraction of instances you predict correctly. Really important problems here are overfitting and generalization. So you want the classifier that does well on the test data, because that's representative of what you'll see in the future. Right. Overfitting refers to the concept of you do really, really well on the training data, but not nearly as well on the test data. That means what you learned is too specific to the training data, and it's not generalizing to data you'll get in the future. So we'll look at this more formally a few lectures from now, if we're able to get that lecture in with the time we have remaining. But we'll look at it at the intuitive level today and kind of build the intuition for what's going on here. I would say this is the most important thing if you apply machine learning in practice, is to be careful about overfitting and generalization, and understanding this cycle here that you have three types of data that you split the original data into: training data that you use for fitting all the parameters, except for those hyperparameters, which are essentially being fit by seeing how well you do on holdout data, and then final performance is reported on separate data, which are called test data. So what's this generalization and overfitting? Here's a simple example. Let's say you are trying to fit a function to this set of points. Right? You might say there's a lot of reasonable choices here. That's true. We don't know what the best one is, but the question is, can you come up with a reasonable fit here? Reasonable meaning you want to do well on data you have not seen before, right? Well, maybe you choose something like a line, or something that roughly looks like this, because that seems reasonable. It's not going through these points exactly, but it might be representative of the pattern that's there. Now, an alternative would be to say, well, I'd like to fit those points a little more closely. Let's fit a degree 15 polynomial, and now it looks like this. And it's very unlikely that the prediction here is any good, because that weird squiggle, same thing over here. And here it keeps shooting up, here it keeps coming down. So unlikely that out there the predictions are any good. So there's a trade-off here in terms of how well you do on the data you're given versus how well you expect to do on data you'll get in the future. What would the experimentation cycle look like on this kind of data? Right? What would it mean to split into training data, held out data, and test data? Effectively, you'd reserve some points as your hold out data. Maybe you'd reserve this point. You do a random split, so maybe you end up with these points as your hold out data. Then maybe you'd end up with another set of points over here as your test data, and everything else would be training data. And your cycle could go something like this. Let's fit a line to the training data. That's 2 parameters. Let's see how well that does on the holdout data. That gives us a number. Store that number. Then let's fit a second order polynomial to the training data. Let's see how well that does on the holdout data. That again gives us a number. We keep doing this, and we change the degree of the polynomial all the way till we think we've seen enough degrees of polynomial. We look at the prediction accuracy on the holdout data, see which one has the best accuracy, and say that's the degree of polynomial we're going to pick. And then we see how well it does on the test data, and hopefully it will be quite similar to what it did on the holdout data, and we're all set. In terms of a question that came up during the break or right after the break, once you're done with this, typically you would do one more pass. You now found the degree of polynomial that's right. You would then throw your holdout data into your training data, so to say, keep the degree of the polynomial fixed, refit it one more time using both train and holdout data, and then see how well you do on the test data to know how well you'd expect to do in the future. And then if you're interested in doing as well as possible in the future, rather than just knowing how well you'll do, you could do the same thing with the test data that you had kept separate. You could also throw that in and now use all the data to fit that specific degree polynomial and use that model for anything that comes to you in the future. The key here is, the main thing here is that you fit the parameters, the coefficients in your polynomial just based on the training data, not based on any other data. You change the degree of the polynomial and pick the best degree based on the holdout data, and that's really the part of the cycle that's most critical here to keep in mind. Okay, so here's another example. Let's look at how overfitting might affect you when you're doing digit classification. So you have here, we're trying to keep a tally of whether it's a 2 or a 3. You might already have your own opinion, but let's see what the algorithm thinks. We're starting out with a prior equal. We'd multiply the probability of on of this particular pixel here, if that's our next pixel, given each class label. Turns out to be the same probability, so they're still on par. This point, the 3 is getting ahead because that pixel being on is much more likely when it's a 3 than when it's a 2. Here, the 3 gets even further ahead because it's very likely for that pixel to be off given it's a 3, much less likely when it's a 2. So 3 is pretty far ahead here. Then last one here that we evaluate is the bottom right, and probability of that being on when it's a 3 is 0, and probability of that being on when it's a 2 is 0.01. We just found out that the probability of this being a 2 according to this calculation will be 1. The probability of this being a 3 is 0 because it's impossible for a 3 to have a on pixel over here because of that 0. How do we end up with this 0? This is what happens if you're in your training data, you never had an on pixel there for a 3. You'd end up with that 0. You'd be overfitting to your training data because you never saw an on there. Doesn't mean it could never happen for a 3. But in this training data set, it was never on that bottom right pixel, so you got a 0. And now a 3 can never be winning out whenever that pixel is on when you classify something. Okay, so it's a different kind of overfitting than the kind of polynomial degree overfitting. It's something where effectively we need to be careful about putting zeros anywhere, because if we put zeros somewhere, then we say things are impossible, and if nevertheless they happen somewhere, then now we're in trouble. Here's another example. So one thing that you might do when you learn a classifier is to look at the ratios. Why would you look at these ratios? What is this saying? The probability of a word, some word W, given ham, over the probability of word W given spam. Remember when we tried to classify something spam versus ham, we essentially take the product of the probabilities of each word given that class label. And so as we running that process, we have a tally where we compare both of them, and the relative contribution to spam versus ham is given by this ratio over here. If that ratio is very high, that word, if it appears, very much contributes to ham being more likely to win out. If that ratio is very low, that has a high effect in terms of making spam more likely to win out in our running product. Okay? And in practice, we'd have logs of these, but still the same idea. Okay, so what you can then do is you can say, well, I learned my classifier. Rather than just looking at, for each class, what's the most likely word, like the, and then off, and then, and so forth. Let's look at this ratio, because wherever this ratio is the highest, those are the words most indicative of a ham email, and allows me to sanity check. what my model learned about most indicative for ham. And then in the second column, we can look at what words are most indicative of observing a spam email, because it really discriminates spam from ham to have a word appear where that ratio is high. Let's take a look. If we use kind of a regular corpus, we actually run this experiment a while ago on corpus, looked at the words in there, looked at the counts, learned those probabilities, then built this table. It turns out all the top entries are infinity, and same thing over here. They're different words, but what's going on here? What's going on is that the top entries here are words where the denominator has a probability of 0. They're words that never appeared, so these are words that never appeared in a spam email. And then these here are words that never appeared in a ham email. As a consequence, the probability is 0. And so if ever you encounter one of those words, you're infinitely sure, so to say, about what the class should be. But of course, that's not right. That's just the classifier being sure, but we don't want that kind of classifier. So these zeros are causing a lot of trouble. Similar to how too high a degree of a polynomial caused trouble by overfitting the train data, this is a different kind of overfitting. Okay, so not happy with this. So what's going on here? If we just use relative frequency parameters, we'll overfit the training data. So we'll say like, well, if this pixel in the corner was never on for a 3, then we'll say it can never be a 3. If that pixel is on, that's overfitting the training data. Same for these words that only appear in one type of email, saying that then that means that other type of email is not possible anymore once you see that word, is overfitting to your corpus that you use for training. You can ask yourself the question, what about words that don't occur in a training set at all? Then both classes will have a probability of 0, which will be even trickier now to make a decision. So in general, we just don't want to be throwing around 0 probabilities. We want to stay away from those. Right? So as an extreme case, you could overfit in a sense that you perfectly get all the training data right, which is you use as a feature whether something is a very specific email. And now that's a great feature for the training data. Say, well, is it this email or not? If so, I saw a label before in the training data. I can say what it is. If it's not an email I've seen in the training data before, now then I have a 0 probability. I won't know what to do with it. So overfitting can happen both in terms of the probabilities we're learning. It can also happen in terms of the features. If you take features that are too specific, like an entire email, that won't generalize to new data either. Okay, so to generalize better, we're going to do something called smoothing or regularization. In statistics, one of the first places this came up was when Laplace was thinking about what's the probability that the sun will rise tomorrow. And even though it's risen every single day in his life, he wanted to have it a non-zero probability that it might not rise the next day, because you never know what could happen. Maybe, it's kind of big star comes in and swoops it away or something. Gravity pulls it. Who knows what could happen? He just didn't want the probability to be 0 that something completely unexpected would happen. So this is a parameter estimation problem. We're estimating the distribution of a random variable. Why? Because asking people for those numbers is hard. They typically won't get good numbers to you, so we'll use our training data to estimate those parameters. And one thing we've seen so far is looking at empirical rates. Let's review what that really means and then go on to how we can smooth those estimates. So let's say we have a bin. There are red marbles and blue marbles. The robot is pulling out 3 marbles. And from pulling out those 3 marbles, we want to effectively have the probability that if in the future another marble gets pulled out, what's the probability of it being red again or the probability of it being blue again? So you could look at those 3. And a reasonable thing to do could be to look at the counts and say, well, how often is it red? How often is it blue? So 2/3, 1/3. That is actually an estimate that's, while very natural, because it's just counting, is something deeper there. It's maximizing the likelihood of the data. Why is that important? Why is it not enough to know that this is just counting? You might encounter probability distributions, models where counting is not the right thing to do, or counting doesn't even make sense, because you might have continuous variables where each value will appear at most once and will never appear again because you have all these real numbers to choose from and there are so many. So the general principle here that will give us the same result but applies to any type of probability distribution where you want to estimate parameters is the maximum likelihood principle. What that does, it says, I'm interested in the likelihood, capital L, of the data, x, under some choice of parameters, theta, that are parameters in my distribution. Now, to make that explicit, we're showing here theta. It's saying there's a probability distribution which has a bunch of free parameters, which are all sitting in a vector theta. And so depending on the choice of those free parameters, these probabilities will be different. And for a given data point and a given choice of parameter vector theta, we can choose the probability of that, compute the probability of that particular data point. So what we're doing here is we're maximizing this quantity. Let's do that for this example to just show how this works. Now, what do we have here? I said we're maximizing over all choices of theta. What are the parameters here? We need to estimate the probability of red versus blue. That's one parameter because the other one will be 1 minus the first one. Let's call that one parameter theta, but in general theta could be a whole vector. So we maximize over all choices of theta. The probability of seeing this under a distribution where we say the probability for blue is theta, the probability for red is 1 minus theta, right? So maximum likelihood, so we're trying to find the maximum likelihood parameter, max over theta, likelihood for x comma theta, which in this case will be max over theta of what's the probability of the first observation? The first one is red. That probability is 1 minus theta. The second one is red. It's independent, so drawn independently, so multiply that in, also 1 minus theta. Then the third one is blue, we multiply in the probability of blue. So we have a quantity here now, a function of theta. For every value of theta, this evaluates to some real number. We can look now at which choice of theta makes this real number the highest. That's our maximum likelihood estimate. How might we do that? Well, we can compute the derivative of this quantity, see where the derivative is 0, and that would be either a maximum, a saddle point, or a minimum, and then we can verify whether it's a maximum, saddle point, or minimum by looking at the second derivative and pick one of the maximums, and among the maximums we would pick the one that achieves the highest value. Okay? Now, in practice with these kind of problems, often taking the derivative gets a little annoying, and it happens to often simplify if instead you look at this problem here. Let's maximize the log of the likelihood of x comma theta. Why is that equivalent? Well, when we take the log of two numbers, if take the log of a and b, if a is bigger than b, the log of a will be bigger than the log of b. So maximizing the log of this quantity is equivalent to maximizing the original quantity. And so because there's a product here, when you take a log, that becomes a sum, and now you'll have a quantity that's a sum of things. And when you take derivatives of sums, they're just the sums of the derivatives, whereas with a product, if you take a derivative, you actually get many, many, many terms that start showing up in the result. So we do this, we maximize over theta, the log of this quantity over here, which is log of 1 minus theta. Let's write this as 1 minus theta squared. Let's put the theta over here, times theta, which is equal to max over theta of 2 log 1 minus theta plus log theta. Okay. Now we can take the derivative with respect to theta. So the derivative of this thing over here with respect to theta. So we look at this quantity here. It's going to be 2 times 1 over 1 minus theta times minus 1 plus 1 over theta. Okay. We want this to be equal to 0 because that's where our function reaches a minimum, maximum, or a saddle point. So we want to set this equal to 0 and solve this for the value or values. There could be more than one of theta that achieve 0. So let's reorganize this. Let's put the minus 1 here. So let's multiply by 1 minus theta and by theta, which gives us minus 2 theta plus 1 minus theta equal 0. So what that gives us now is we have 1 minus 3 theta equals 0, which we can solve for theta, and we see theta equals 1/3 to achieve 0 here. So we see the probability of blue is 1/3 according to our maximum likelihood estimate, which is exactly our count. You could have just counted and got that result, but this is showing that there's a more general principle here, where what you're looking at is, among all choices of parameters, you pick that choice that maximizes that you get to see the data that you just saw, which is a much more general principle than computing counts from your data. Any questions about likelihood and maximum likelihood? Yes?
This might be a weird question, but in that equation, like for the likelihood of x and theta, did you actually use x?
Okay, so that's a great question. X here is referring to the data, and so we're using the x corresponds to this information over here that we saw red, red, blue. So x is encoding that. X is a vector where the first entry is saying red, second entry is saying red, third entry is saying blue, and we're using that here when we compute the likelihood. We're saying the way we compose the likelihood is we look at each data point and we multiply together the probability of observing that data point. So the first factor here is 1 minus theta, that's the probability of red, the first data point, times the probability of the second data point, times the probability of the third data point. So that's where x comes in. And that will always come back whenever you try to express the likelihood of some data. You'll have to look at each data point at a time, assuming they're independently drawn, and multiply the probabilities together, where the probability is expressed using the parameters you're trying to recover. If there are features, you can do the same thing. So to make that more explicit, if you were to look at the likelihood of something with features, your likelihood would now look like maybe there is the probability, which depends on your parameter vector theta, of ham, which was your first label, let's say, and then times the probability of word 1 given ham, times the probability of word 2 given ham, but theta would be sitting here and here, and you would then look what that theta is, and maybe this, you would have the first theta could be, maybe you'd call it theta ham, and then this one here, maybe you'd call it theta for word 1 given ham, and so forth. And so your theta vector would have entries for each of those possible probabilities that you care about, and you'd have an expression that multiplies those together. Yes?
So you mentioned that our model should never assign probability of 0 to an event we haven't seen. But it seems like here the probability of drawing a green marble using this metric would be 0, right?
Correct.
So how do you actually correct for that?
Next slide. Great question. So we still have the same problem here, but we've now put our estimation procedure in kind of a bigger context to something that we can do for any type of problem. Now we'll start worrying about how we deal with getting rid of the zeros. So what we need is smoothing. Smoothing out really dangerous light rays coming at you. Now, maximum likelihood looked like this. We'll call it theta ml. ml here stands for maximum likelihood. Is the theta that maximizes this quantity here. This here, argmax, stands for I'm solving a maximization problem, and rather than returning the value of the maximum, I'm returning the argument, the theta that achieves that maximum. So argmax over theta is saying solve an optimization problem, but don't return the value you get there, but return the theta that achieves it. That's what the arg up front here is doing for you. So what that would look like in general is a product of probabilities of each of your data points under your distribution that you're using, which is parameterized by theta. If you calculate the derivative, you set it equal to 0. Usually you would look at the log because the calculation will be easier. You'll find for simple models that you just have to count over the number of samples. Okay. Now, another thing you could do, which is a variant on this, which essentially will start smoothing things out for us, is to look at the maximum a posteriori, MAP, max a posteriori estimate. It's not the maximum likelihood estimate, it's the maximum a posteriori estimate, where you say, well, instead of maximizing the likelihood of the data for a given choice of parameter and then find the parameter choice that makes that highest, let's look at what's the distribution over parameter values given the data I've seen, and pick the one that maximizes that. Now we apply Bayes' rule and see that this is the likelihood times the prior divided by the probability of the data. Okay. Now we're interested in the theta value that maximizes this. Theta does not appear in here, so we can get rid of that when we're just interested in finding the theta that maximizes this expression. And we're looking at the argmax of this thing over here. And so what you have now is the ability to put in a prior over theta. You could say a theta that has any entry that's 0 has actually 0 probability. You could encode that in your prior, and now you'd stay away from anything that puts zeros anywhere. So anything you know about your parameter vector theta ahead of time, you would encode in that prior. And then when you use the map estimate, that information would be used. Again, the most typical thing would be something like ensuring you stay away from 0, but there could be other information you have about theta, and you can generically put it in your prior and then get a new estimate out, which won't necessarily be exactly counts, but it'll be something that is the right thing based on both the data and your prior over what you think the parameter vector should be. Okay, so this is pretty generic. You can apply this anywhere. Let's look at some specific case kind of implementations of this where we stay away from 0. So this is the Laplace story. He wanted to account for the fact that maybe the sun wouldn't rise one day and invented Laplace smoothing. So what is Laplace smoothing? What you do here is you estimate, based on the data you have, the probability of red versus the probability of blue. The maximum likelihood estimate would just be 2/3, 1/3. The Laplace estimate says, because I want to account for every possible thing to have some non-zero probability, I'm going to augment my training data and effectively add a fake red and a fake blue to it, and then run maximum likelihood. Or mathematically, when you are counting things, you have a +1 in your count for any specific value. And of course, when you normalize, you take the sum over all counts, you need to add a +1 here whenever counting each possible outcome too. And so the equation you end up with looks like this, where this here stands for the number of values x can take on. So if it's binary, that thing here would be a 2. If it's a random variable that can take on 10 values, like in digit classification, that would be 10. So the Laplace estimate here would not be 2/3, 1/3, but would be 3/5, 2/5. Okay? So one way to think of this is as you're just adding fake data to your training data, which is encoding your prior information that you say, these things are possible, these things can happen. I didn't see them in the training data or not. Maybe I saw some things here, but I wanted to say, well, I think half-half is most likely as I start out, so I'm going to throw in one of each to bias the estimate that I get towards what I thought would be most likely before having seen the data, right? You can formally derive this, doing this procedure as having a prior over theta that is of a specific format that you multiply in with your likelihood to then get the maximum a posteriori, and then the maximum a posteriori for the right prior will coincide with the Laplace estimate, just like the maximum likelihood estimate corresponded with the regular counts. Okay, let's look at another example here. You can do this not just by adding 1, but you could add any number k. So k here is a free parameter. That's our first example of a hyperparameter. The degree of the polynomial was another example, but we don't do a lot of polynomial fitting here. We tend to fit probability distributions. So this is our first hyperparameter in fitting distributions. So k is a choice. We had k equal 1 on this slide over here. Just if people say Laplace smoothing, they mean they use k equal to 1, but in general there's something called Laplace smoothing with k equal to a different number than necessarily 1. If k equals 0, what happens? It doesn't contribute. You're back to the maximum likelihood estimates. If k equals 1, you have what was on the previous slide. So this is k equals 0, k equals 1. But if you say, a priori, I think red and blue are equally likely, and I need to see a lot of evidence that shows otherwise before I would believe it, you could throw in a prior where you say, I think I've already seen 100 reds, I've seen 100 blues. That's where I start from. I've actually not seen those, but that's my prior. That's how I encode what I know about the world, and then use an estimate, Laplace estimate with k equal 100, and you end up with something that's still very close to 50-50, even though the data says 2/3, 1/3. Okay? Again, you can encode this in a prior distribution if you like. 281 covers how to do that formally, and then the maxima a posteriori would coincide with the Laplace estimate. So in general, this is what it would look like. Now, one tricky part with doing Laplace estimation is that in some sense it's somewhat naive. You're just saying, well, I'm just going to throw in something I think I know about the data, but what if x and y are very, very large, and you try to estimate a conditional, right? It might be that once you throw in that prior information, you get some data. You're pretty much still at the prior, and you're not using your data maybe nearly as effectively as you'd like to. But then if you fully use it with maximum likelihood, you end up with overfitting, and you end up with zeros and so forth. So there's something in between you can do, which is effectively smoothing out your distribution. What is this saying? This here is saying that I'm going to compute the conditional of x given y by an average, a weighted average of what I get from the counts, or maybe a Laplace estimate, whatever way I estimate x given y, but then smooth it out with the prior distribution for x. Why is this interesting? Well, if y is very large, you might not see combinations of certain x's with certain y's at all in your data, or not much of it. But you might say, well, I still want to use that in general. Certain x's are more likely than other x's, and you essentially compute that over here by just looking at the counts for the x's, or whatever estimate you just did for the distribution for x, and then use that to smooth out your distribution for x given y. Right? So this can often give you better estimates. Think of, for example, the spam versus ham example. Maybe you look at a large corpus where you see how often each word appears. Use that as your prior for each word. Use that to smooth your estimate of a particular word given a particular class label to get it closer to the right probability. Okay, so here's what happens when you use smoothing. We then order the features by the odds ratios. We see that the most indicative of ham versus spam is Helvetica, then seams, then group, and so forth. No infinities anymore. These are reasonable numbers. And then same here, the most indicative words for spam over ham. Makes a lot more sense. You could still argue with whether these are really perfect, but I mean, maybe you don't have enough data. You need more data to get something that you believe even more. That'll depend on the task you're looking at. Okay. So the one thing we now have to do, now we have those hyperparameters, we need to tune them, right? So let's go back to the original picture we had, which I said is essentially the most important picture when you're doing machine learning. You split your data in training data, held out data, test data. You would use your training data to train the parameters. Let's say your entire theta vector is estimated based on the training data. How you estimate that theta vector is determined by some hyperparameters. What alpha are you using? What k are you using? What model are you using? What basenet? And so forth. Many choices there. Now, if it's a continuous parameter, often the pattern you'll see is, if this is your parameter k, which is your Laplace smoothing, the more you smooth, the less you're fitting your training data. So the top curve here for training data is pretty clear. What's happening is you're less and less able to fit your training data because you're not allowing it to. You're smoothing it towards whatever your prior was. And so the accuracy on your training data will drop as you smooth more. In general, as you regularize more, meaning you put a stronger prior in there, you let it less closely fit the data you have. Now, as you sweep that parameter and you make that curve, what you'll see is that on your holdout data, the pattern will be different. Initially, you'd be overfitting your training data in many cases. You get a certain level of performance on your holdout data that's quite a bit lower than your training data performance. And as you regularize more and more, your training data performance will drop a bit because you're not fitting your training data as well, but your holdout performance will go up because you're now fitting your parameters in a way that generalizes better. At some point this will peak, in this case somewhere over here, and after that you're regularizing so much that you're not using your data all that well, and even on the holdout data you're starting to do worse now because just you're not using much information from your data, you're just close to your prior, or you're just kind of smoothing things completely, and performance drops for holdout data too. So the spot you pick is this spot over here. That'd be your choice of k. You might have to do this for multiple parameters. So you might have a higher dimensional plot than just a 2D plot here, or 1D, depending how you count. And then the hope would be that as you look at your test data, that actually the test data will behave very similarly to your holdout data. This will typically be the case. It won't be exactly peaking at the same spot, but roughly at the same spot. And so choosing based on the holdout data is a good way to get there. Now keep one thing in mind. The reason this plays out is because there's a small number of hyperparameters you're tuning with your holdout data, and that's why your holdout data is so representative of your test data, right? If you start choosing millions of hyperparameters, you just call your original parameters hyperparameters, a slight change of name, and you start choosing them based on your holdout data, then your holdout data will not be representative anymore of your test data. You'll lose this property. So be wary of the fact that the bulk of your parameters should be chosen based on the training data, and then a few leftover parameters based on your holdout data. Okay. So the main thing left in practice then, once you know this procedure, you have everything implemented, is choosing features. And so often what will happen is you'll get errors, and you're going to have to go through a cycle of, well, things are not working. I tried every possible hyperparameter setting. Things are still not working. What to do now? Actually, this is too important to try to cover in the last 2 minutes, so let's cover this in one of the next lectures. This is it for today.